I'm pleased to introduce our speaker today, Mike Spall, physical oceanographer and senior scientist at Woods Hole Oceanographic Institution. Mike has participated in the US Science Team for many years now, having joined in 2013, and serving as the co-lead of Task Team 3 on AMOC mechanisms and predictability since 2017. And in keeping with the focus of Task Team 3, Mike will be presenting today on wind-driven variability of the meridional overturning circulation. And I'm going to hand off to you, Mike, to get started.
Okay, great. Thank you. Well, I think for this audience, I don't need to go into a lot of detail on motivation and background, but there are a few points I want to highlight just so we're all off on the same page. The rapid MOC array 26.5 north shows variability of the AMOC on timescales essentially from weeks to the instrument record, which is now over 10 years. Some model simulations suggest that the variability of the AMOC is dominated by external forcing. There is some internal variability, but at pretty much all latitudes, and especially away from the Gulf Stream separation latitude, at least in this one kind of high-resolution numerical model, the variability is dominated by atmospheric forcing. That's not to say that there aren't coupled modes, but in terms of this model, it's coming from atmospheric forcing. So there were a few papers about 5 years ago looking at simple two-layer wind-forced models, and they found that those models could reproduce most of the AMOC variability on seasonal to interannual timescales. These paper by Zhao and Johns, there were two papers there and one by Jian Yang. And in this paper by Jian, he found in particular that wind stress anomalies in the subpolar gyre were important for AMOC variability at subtropical gyre latitudes by inserting walls that would kind of block communication. So as we'll see, that's kind of the focus of my talk, is this kind of remote forcing of the AMOC. So I'm going to do some of these two-layer model calculations. They're more idealized than these previous studies. Just integrating the shallow water equations. There's wind forcing in layer 1, that's this tau. I have a horizontal viscosity. And there's a continuity equation. There's no diapicnal mixing. So mass is conserved in each of these layers. For most of what I'm going to talk about, it's a closed domain with no slip and no normal flow boundary conditions. I will mention briefly some results that has a mean deep western boundary current. So there's an exchange through the northern and southern boundaries. So my model domain is here. It's just a rectangle. It's 6,000 kilometers in zonal extent, 9,000 kilometers in meridional extent. The equator sits here. So I have 6,000 kilometers in the northern hemisphere. It's a flat bottom. The wind stress is just representing a subpolar and a subtropical gyre. They're symmetric here, given by this cosine function. Graphically, these little white vectors indicate the wind stress pattern, and it's independent of longitude. I've only shown it at this one location, but it's uniform in longitude. And it's modulated with a period P and an amplitude, non-dimensional amplitude of alpha. So I'm just going to initialize the model with equal layer thicknesses. I'm going to force it with this periodic wind stress. It takes typically 20 or 30 years to kind of settle down to an equilibrium cycle. Some of the cases I'm going to do have very low frequency forcing, so in those cases I'm running the model out to 200 years. And by AMOC, I'm talking about the meridional transport in layer 2, which is essentially equal and opposite to the meridional transport in layer 1 because my sea surface is pretty stiff, so there's not really much total mass accumulation in either of the basins. This is the mean transport stream function. For my central case, it's about 35 sphere drips. Okay, so if we look at the time series of the overturning circulation at the gyre boundary, this black line, and at the southern limit of the subtropical gyre in this red line, it looks like this. This is a 50-year integration. The black line here is the gyre boundary. So it's got an amplitude of about plus or minus 2.2 sphere drips. The dashed line here is the wind stress amplitude times 10, just so it'll fit on the graph. And you can kind of see the phase. But what's interesting here is the red line is the overturning at the southern limit of the subtropical gyre. So this black line, if we just calculate the Ekman transport at the gyre boundary right here, the black line is essentially the barotropic return flow. So that mechanism's been recognized for quite a while. You've got southward Ekman transport, you've got a barotropic northward flow in each of the layers. It manifests in layer 2 at about half of what the Ekman transport is, which is about 4.2 spheredrups. But if that were all that was going on, then we'd expect the overturn to be 0 at this latitude because there's no Ekman transport at that latitude. But we can see it's almost half of the maximum at mid-latitudes. So I'm going to refer to this red line, the meridional transport or overturning at the southern limit of the subtropical gyre, as the remotely forced MOC. And that's going to be the main focus of what I'm trying to understand. So now I've taken the model and I've done a bunch of calculations where I varied the forcing period P, and I've scaled the overturning by that Ekman transport at the gyre boundary, which here is about 4 spheredrups. And I'm plotting the magnitude of the overturning variability as a function of latitude here and non-dimensional frequency here. So this is the frequency, it's the time it takes the Ross wave to cross the basin divided by the forcing period. So a 10 to the 0 means that I'm oscillating the period at exactly the time it takes a Ross wave to cross the gyre at the gyre boundary, to cross the basin. So at high frequencies up here, the maximum is about 0.5, which is just this barotropic response that I talked about. It's confined to the latitude range of the wind stress anomaly. This dashed line is the southern limit of the subtropical gyre. It stays about that magnitude until we reach this basin crossing time scale. It increases slightly here, but the main feature is now we see an overturning circulation extending well south of the wind stress anomaly, even into the southern hemisphere. At low frequencies, even at the latitude of the wind, it decays to 0. So we expect that, because at very low frequency forcing, all the wind-driven circulation is in the upper layer and the deep layer is motionless. So we expect very little response at the lowest frequencies. But this is the feature I want to look at right here. So just to see how general this result was, I did a whole bunch of calculations. I varied beta, I varied G prime, and I varied the forcing period, P. And I'm plotting them as a function of 1 over the period. This is now dimensional. So that's 1 year, 10 years, 100 years. And I'm plotting the amplitude of the overturning stream function variability. The black ones are at the gyre boundary. They go from about 2 spheredrups up to 5 spheredrups. And the red ones, red symbols, are the remote forcing. And that's roughly half of what the gyre boundary is. If I scale these things, now I'm scaling the overturning by this Ekman transport variability, and I'm scaling the frequency by this basin crossing time scale, all these symbols pretty much collapse onto these 2 curves, which look a lot like the figure I just showed you. At the gyre boundary, it's about half. That's the barotropic response. It goes up a little bit around the basin crossing time scale, and then it decays to 0. And the remote forcing decays at low frequency, decays at high frequency, and it peaks around this basin crossing time scale. And it's about 1/2 the basin crossing time scale where the peak is. All right, so I think this is a general, I think this is a general pattern, a general behavior. So now I want to describe what I think is going on. This is the mean layer thickness in layer 2 for that case with the 10-year period forcing. You can see the interface displacement in the subpolar gyre is much larger than it is in the subtropical gyre. And that's easy. It's just what's required to balance the spheredrup transport. Because F is larger at higher latitudes, we need a larger interface displacement to balance the same meridional transport. So these are essentially just spheredrup balances. But because F is larger, we need more interface displacement here. Now, if we think of the lowest frequency forcing, it's just going to oscillate back and forth between circulations that are in equilibrium with the wind stress curl. So at the strongest forcing, you're going to have the largest interface displacement. The weakest forcing, you have small interface displacement. If I just calculate that change in layer 2 thickness over the forcing period, it looks like this. So a small variation in the subtropical gyre and a large variation in the subpolar gyre. So in order to accommodate geostrophy and to arrive at these equilibrium states, the subpolar gyre retains and expels more fluid than can be accepted or provided by the subtropical gyre, because they both need to stay in geostrophic balance. The difference between those two volumes divided by the time it takes to transition from one state to the other is the remote forced MOC. So it's a change in volume divided by a change in time. Also in this figure, you can see that the change in layer thickness along the eastern boundary is very small. So I'm going to assume that's constant. It's not quite, but it's pretty small. Okay, so if we just look at the layer thickness, this is now layer 1 thickness, that balances a transport psi, it looks like this. Psi is a function of x now. If we assume that this quantity is small, it's approximately given by this. This quantity being small says that the interface displacement is small compared to the mean layer thickness, or layer thickness on the eastern boundary. So if we just consider the change in volume when psi is large compared to the change in volume when psi is small, integrate over both the subtropical and the subpolar gyres, we get a change in volume. I'm using this approximation here. This change in volume just looks like this. That's the wind stress anomaly. That's the meridional scale over which the winds vary. That's the zonal extent of the basin. G prime and H1E is the thickness on the eastern boundary. So for long forcing periods, it changes by that amount of volume over 1/2 of the forcing period. That's how long it takes to go from the maximum to the minimum. And I've tossed in a scale factor of pi over 2 because that would be the average. And if I want to get the maximum transport, it would scale with pi over 2 times that. All right, so that's an estimate for the overturning that would happen on long time scales. If I scale that by the Ekman transport, and if I assume my layer thicknesses are about equal, all it depends on is the ratio of this meridional length scale over which the winds vary to the latitude of the winds. It doesn't depend on beta, it doesn't depend on G prime. The Rossway phase speed actually isn't very important. That's buried in here. So that explains why all those calculations I did, those 60-some calculations, all fell on the same curves, because I kept these quantities the same. I was just varying the physical parameters. Okay, so now let's consider some time dependence. So if the forcing period is short compared to the basin crossing timescale, then the wind stress changes before the Ross wave has crossed the whole basin. So it begins to adjust, but then it changes again. So the fraction of the basin that has adjusted is going to scale linearly with the ratio of this forcing period to the basin crossing timescale. So now I've kind of piled all this stuff together here. That's that delta V. This top, I'm choosing if the period, half the period is smaller than the crossing timescale, then I reduce the volume by that linear fraction. And then if the forcing period is long compared to the basin crossing timescale, then the change in volume takes place over half the forcing period. So this is kind of a heuristic model. I'm doing a little bit of hand waving here, but I think that this is essentially what's controlling the behavior and the amplitude of the frequency. The frequency and magnitude dependence of the remote overturning. So now along this dashed line, that's the southern limit of the subtropical gyre. I'm plotting results from the theory, which is that black line. Diagnosed from this series of model calculations is the red line. And I'm shocked by how well they agree, given my model is not really formal. It's maximum about 45% of the Ekman transport and decays linearly with higher and lower frequencies. This blue line is with a mean deep western boundary current. Essentially doesn't do anything. It looks just like this plot here. There's a little bit of enhancement at very high frequencies. I'm running a little bit short on time, so I'm going to go quickly through these. Where does the variability take place? At the gyre boundary at high frequencies, it's all the way across the gyre. So this is the magnitude of the variability as a function of frequency and longitude. As we transition to this basin crossing time scale, the frequency shifts to the west, and we go to lower frequencies, it continues to shift to the west. It's all accumulated here. If the lines are horizontal, it means there's no additional variability in the interior, so all the variance is to the west of that. At 1,000 kilometers north of the equator, there's very little high frequency. All the variability is accumulated here in the western boundary current. There's a little bit of reverse flow here. That's waves radiating off the eastern boundary that are out of phase. And in the southern hemisphere, it's all in the interior, all the variability. So if I force things more strongly, this is now the interface displacement. I can get a region of closed PV contours. You can track the phase propagation of these features. They know about this bending of the PV contours. I don't have time to go into details on that. But if I do the same analysis, it still agrees quite well. Then the last thing I wanted to talk about, if I add a deep western boundary current, now I get this pattern, which is going to be compared with this. I get higher variability at all frequencies and at all latitudes. Now they even extend all the way to my southern boundary, so it's exchanging with the Southern Ocean. At the southern boundary latitude, it's this blue line, so you can see there's an enhancement all the way around. The mechanism behind that, I don't really have a theory for it, but I can describe what happens. Here, the mean deep western boundary current is diverted into the interior because there's such a big PV barrier here. So this is the mean transport stream function in layer 2. You can see deep western boundary current comes in here, diverts off into the interior, comes back to the boundary, and goes back out to south. So as the winds fluctuate up and down, this region expands and contracts. As it does, it pulls boundary current water off or sends it back to the deep western boundary current, and then that is imported and exported, that anomaly is, to all the other latitudes. So this is really an enhancement of the mid-latitude storage of mass, in addition to the wind-driven gyres. Okay, I hope I didn't go too fast through some of that, but hopefully you get the message. Within the latitude range of the wind stress anomalies, the MOC variability is dominated by a barotropic mode. At high frequencies, it's confined to the latitude range of the wind stress anomalies. It goes to 0 at low frequencies. We get a significant remotely forced MOC for forcing periods near the basin crossing time scale. Decays linearly, both higher and lower frequency. And the basic mechanism is geostrophy and Rosswave phase speed that slows down at higher latitudes. That gives rise to a mass imbalance between the subtropical and the subpolar gyre, and the only way that can be accommodated is by transport from the western boundary current. So that's how it gets out to the rest of the world. In the nonlinear regime, the simple linear theory works really well, but the deep western boundary current becomes more important because then it doesn't stay attached to the western boundary, but it gets diverted off into the interior. So there it is, 20 minutes. Let's have some questions.
Thanks, Mike. So yes, let's open the floor. Just raise your hand and I'll take you off mute. So Paula, I'm going to get you. Hold on. I don't see your number below. Hold on. There we go. Okay, you're unmuted. Go ahead, Paula. Paola, we can't hear you. You might be on mute on your phone. Try that.
Do you hear me now?
Yes, thank you. There you go.
Okay. So my question is, Mike, sorry, I'm getting this. Okay.
We can hear you.
No, I know, but there was just some stupid voice talking to me saying that this was recorded. So my question is, your layer, your lower layer does not outcrop, right?
That's right.
So I think the classical adiabatic theory of the AMOC, that is a pretty important ingredient. So I wondered if things would change a lot if that was allowed, the outcrop of the lower layer.
Yeah, let's see. So if my adjustment relies on startup balance. So I think once things outcrop, that portion of the domain, the layer thickness can't change, right? So it would be muted. The response would be weakened once the layer outcrops, because then the volume of layer 1, for example, won't change because it's already at its minimum. So yes, I think outcrops will reduce the amplitude.
Okay. So
probably linearly with the outcrop area, but I can't be certain of that.
Okay, so I'm going to move on to our next question from Aksu Hu. I've just unmuted you.
Okay, hi, this is Aishu. Mark, this is a very, very interesting talk, and I have a question I want you to clarify. Since you have this two-layer model, I assume for the upper layer you have a mean northward flow, and the lower layer you have a mean southward flow. Is that right?
Only for the cases that have a mean deep western boundary current. So most of what I showed, the basin was closed on all boundaries, so there was no mean northward and southward flow. But I did do calculations that have imposed a mean deep western boundary current. And in those cases, what you said is correct. For the weak forcing case, the mean deep western boundary current just stays on the western boundary, and it really doesn't influence the results at all.
Okay. Another thing I want to ask you is because in this model you have the only forcing you applied is the wind. Do you think anything like the density change can affect your result?
Buoyancy forcing, you mean?
Mm-hmm. Yeah.
Yeah, that's a good question. I don't think so, at least not as it would be parameterized in this sort of layer model, because that would just kind of move the interface. It would be a local transformation of layer 1 fluid to layer 2 fluid.
Mm-hmm.
So the mass budget would always be closed, just be moving the interface up and down. To the extent that it modifies the Rossby wave phase speed and the adjustment timescales, then it might impact things. Offhand, I can't really anticipate exactly how. I think it would probably shift the peak amplitude a little bit in frequency space.
Okay. And here for the Rossby adjustment, the time scale, is it like 10, 20 years or longer?
Oh, it just depends on the parameters I chose. So, things scale with that basin crossing time scale, and I've done calculations in which it's 5 years. I've done in which it's 30 years. That whole suite of calculations I showed that had quite a wide range of time scales.
Oh, okay. Great. Thank you.
So we've got a number of other people just raise their hands. Dan, I'm going to take you off mute. Here we go.
Okay.
And I'm right. Here you
Great. Yeah, thanks, Mike. I was wondering if you could, I guess I'm curious about the intermediative role of the Rossby transport timescale. Does that introduce a lag in the variability that you see, sort of the remote variability? And also, is the system linear in the sense that you force it with a particular wind stress period in time, and the response also has that period in time?
Yes to the second question. These are non-eddy resolving calculations, so everything, I do get some internal variability, so I can get some higher frequency variability, but actually everything I've showed, I didn't say, but everything I've showed has been bandpass filtered, so I'm picking out the forcing frequency. What was the first part of the question?
The first part of the question was about lags.
Yeah, there are some lags, and I hinted at that in that first time series I showed. They're fairly complicated, and I haven't really tried to predict them in any kind of simple way. But you clearly see phase lags in one of these figures, this one here. This one, you can see there's a phase shift. So the variability is a maximum over here, and it decreases. Mm-hmm. So when stuff's going south here, some's going north here, and that comes from the waves being radiated off the eastern boundary. And in fact, here you can see a maximum and a minimum, and that is kind of a resonance with the wave crossing the boundary. So there are phase lags. I don't have a simple explanation for what they are, though, because it's kind of complicated. So I ended up choosing the gyre boundary as my time scale, but it's faster than that to the south. It's slower than that to the north. So I did that just so I could have something kind of simple and compact and intuitive, but in reality, I think it's more complicated.
Mm-hmm. Okay, thanks.
Okay, we have a question from Luann Thompson. Go ahead, Luann.
Yeah. Hi, Mike. I was wondering about the influence of topography on the eastern or western boundary. In particular, the boundary layers are viscous here, I assume, in the west. I know it's a complication, but I was just curious about your thoughts.
Oh, sorry. Mike, you were muted. Sorry about that.
Sure. I think the topography, if we consider a little bit away from the boundaries, it can guide the Rossby waves. So that may modify these ray paths and the adjustment pathways, but I think the big picture would still hold. The eastern boundary, if we had some topography over there, it may modify the boundary waves, but they're going to be fast anyway. So I don't think that really matters as long as they're fast. And probably similarly on the western boundary. So the configuration I've chosen is idealized in almost every way possible, but the mechanism I think is much more general than that. So I chose this idealized framework just so I could get simple analytic solutions and kind of make things intuitive. But I can't really think of what would break making things more complicated in terms of topography and spatially more variable forcing and things like that. It's really just geostrophy and wave speeds being a function of latitude. So that's a long-winded answer to say I'm not really sure, but I think you could still apply the same ideas.
Okay, and let's take one final question then from Marlos. Goes.
Hello, Mike. Nice talk. I just had two simple questions here. So what do you do with the Ekman forcing? So you assume the whole first layer, the Ekman influence the whole. Yeah.
Yep.
So it's variable, the first layer. And so what? Sorry.
I was going to say, yeah, the Ekman transport is distributed over the entire first layer. So if I have a southward Ekman transport of, say, 1, and I have a barotropic return flow of 1, half of that is in the deep layer, and half of it's in the upper layer. So I have a net southward transfer in the upper layer of a half, and a northward transfer in a deep layer of a half, which is why I'm getting a half for my high-frequency MOC, because the Ekman and the barotropic component partly cancel.
I see. And so what did you say about the eddy? So can you, varying your parameters, can you resolve eddies? Oh,
I don't resolve eddies in any of these calculations. My grid spacing is 40 kilometers. But eddies do emerge for some cases. It's still baroclinically unstable, even though it's quite dissipative. So I could do the same thing, at 10 kilometers or something like that. But I did so many of these calculations and out to 200 years, and I think the basic mechanism doesn't rely on eddies, that I thought it was useful just to look at kind of the linear wave regime first. Offhand, I'm not sure what the eddies would do, but that would be I think a useful direction to go in from here.
Right. Okay. Yeah. Thank you.
Okay, and thank you, Mike, for your webinar, and thanks to everyone else for joining. We had more than 30 participants, which is one of the largest AMOC webinar turnouts to date. Tune in next month for our June AMOC webinar. It's scheduled for noon on June 20th. We're still looking for a presenter, so if you would like to present to the group, please reach out to Jenny Zhu or myself, and we'll get it lined up. Okay, take care, everyone.